So we are now starting into chapter 3. This is a very different chapter than what we've been doing so far. So far, I would consider that to be the easy stuff. And I'm not saying this to scare you. I think I told you on day 1, this is not an easy class. And although some of the chapter 1 and chapter 2 material was easy for a lot of you, it just gets a little more challenging and a little bit more difficult as we move on. And some students find that this is perhaps one of the more challenging chapters. There is a lot of math involved in this chapter, but we're not doing the math. In fact, there's no mathematical calculations that I'm going to have you do for chapter 3. That may be good news, okay? There'll be plenty of math coming up, but there's still a lot of really difficult concepts because we're talking about quantum theory here. And quantum theory is really, really difficult stuff. We're not going to get that deep into it, but I am going to expose you to enough of it to hopefully at least let you understand what was involved, what was some of the scientific method that was going on at the time to get scientists to come up with new models of atomic structure that we now use today and for many cases kind of take for granted. This is our picture of the plum pudding model that Rutherford's lab quickly disproved. He came up with the Rutherford model of the atom, which of course has the dense nucleus at the center of the atom. Takes up most all of the mass of the atom, but hardly any of the volume. And then surrounded by the nucleus, we have the electrons that are sort of drawn in orbit around that nucleus. And the electrons have hardly any mass at all, but they take up almost all of the volume. And we still use this model today. As I've mentioned before, you can see it on the banners in the courtyard of the building. But this is really not an accurate depiction of atomic structure, even though we still use this model, because it is very useful. It shows that it's mostly empty space. It shows where the protons and neutrons are located in the nucleus, right? But we are now going to be learning about quantum theory in this chapter. And we will be continuing along with the scientific method. I'm going to show you a few more experiments, or at least models from experiments. And for example, we'll be talking today about the Bohr model, which looks like this. And we still have electrons that are in orbit around a central nucleus. I mean, they were modifying. They were always building upon the previous models. So we still have a positively charged nucleus with electrons out here in orbit, but now we'll have different energy levels for those orbits. And those energy levels are going to be quantized. It's not a continuum of energy levels. It's either found at energy level 1, energy level 2, or energy level 3. Right? So these are now going to be quantized energy levels. And we're not going to have electrons in orbit anymore. We're going to even go beyond the Bohr model in this chapter and start coming up with a new concept of how electrons are organized in atoms, and we call those orbitals. And this is just one graphical depiction. Orbitals, this is going to be a theoretical, it's a probability where you might find an electron at a given time, right? It's a probability distribution. And we're going to learn how to describe where these electrons are found within these different quantized energy levels, right? That's part of learning the symbols, right? Because we can't really see where these electrons are. So we're going to use symbols and models to help us understand what's happening at a level that we can't see. That's what models are all about. All right, so that's where we're going in this chapter. All right, but there's some very, very interesting experiments that I talked about in the video content, and it has to do with what the physicists at the time were learning about the nature of light. And we talk a lot about Maxwell's electromagnetic radiation. I talk about the Thomas Young double slit experiment, very famous experiment, all right? We talk about Max Planck whose name is spelled wrong on this slide, but I think in the one that I gave you, it's spelled right now. Oh, there, I spelled it right down below. And lots of little equations here. We won't be doing math with these equations, but I do want you to understand what those equations mean and what they represent and what the symbols in those equations represent. All right. But the main point that I want to bring forward from that video content is that for over 100 years, scientists thought that light behaved as a wave. Okay. And it wasn't until Albert Einstein came along and explained the photoelectric effect that we had this notion that electrons could also behave as particles as well as waves. And I mention that because so far our discussion, let me just cut down here to this slide here. Our discussion from chapter 2, right, from the chemistry side of things, right? We did J.J. Thomson's experiment on the left and Millikan's experiment. Then we got into the plum pudding and Rutherford. This was always treating electrons as particles. All throughout our discussion so far from chapter 2. So all of this stuff, these figures kind of summarize where we are right now in our class discussion on the atomic models, okay? And it's all with the idea. All of the evidence supports the idea that electrons are particles, they have mass, right? That was Millikan's experiment, the mass and the charge separated that out, right? And then this idea that the electrons are out there as little raisins in the pudding, so to speak. So just like with light, that they thought for over 100 years, light was a wave, and then Einstein comes along and says, hey, it might be a particle too. In fact, we can think of it both ways. So the same thing's going to happen here with the electron. We're working with all of this experimental data, thinking that electrons are particles. And the revolutionary step that I should get to by the end of this lecture is that, hey, maybe it also behaves like a wave. And if we think about electrons also behaving as a wave as well as a particle, that might explain a lot of the scientific data that we're trying to make sense of. Okay, so that's kind of a summary of today's lecture. So now let's explore some more of the details of that. And it starts again with this idea of how light behaves, but now light that's generated from chemical elements. And it's a very simple experiment where you take light and you refract it through a prism and you get the rainbow. I'm sure you've all played with prisms before, right? Everyone, right? Hold it up to your eye, it's really pretty, right? See things. All right, so if you actually do that with sunlight, okay, and you refract the sunlight through a prism and you look very, very carefully at the spectrum, you don't actually see a full, complete spectrum. You've got these dark lines throughout the spectrum. And in fact, they're very reproducible dark lines. Reproducible dark lines in the spectrum that comes out from doing this experiment. All right, and von Fraunhofer actually spent a lot of time very, very carefully characterizing all of these dark lines in the spectrum. This was all done in the early 1800s, by the way, just to put some historical perspective on here, okay? So von Fraunhofer actually mapped these dark lines, mapped and characterized. All of these dark lines. Now, that doesn't mean that they understood where the dark lines came from, but the fact that they were so reproducible and measurable made them think that, okay, something's causing this, we need to figure out what's going on. Can we explain the underlying theory, right? The theory explains, it gives you the how and why of the observation. All right, so let's take it a little step further. If we take, instead of sunlight, if we just take the light that comes from burning hydrogen gas, right? And this is what was done from Bunsen and Kirchhoff. Many of you might recognize the name Bunsen, as in your Bunsen burners that you've been using in lab, okay? It's the same person, all right? So they took their Bunsen burner. Let's draw a little picture of a Bunsen burner here. And instead of generating sunlight, we're gonna generate light from a hydrogen flame. So we're gonna take some hydrogen gas here. And by the way, you'll learn this soon enough, but hydrogen, when it's by itself in nature, actually forms a molecule, H2. So this is hydrogen gas, right? And if we take the light that comes from hydrogen gas and refract that through a prism and look at the spectrum that comes out, okay? Let me zoom in on this. This is what we get. We don't get a full spectrum of colors. We only get 4 what we call spectral lines. And hopefully you can see them here in the lecture hall. Now remember, this is light. And going back to the video content, all right, with Maxwell, right, we're thinking of light as electromagnetic radiation. Right, and that light, we can talk about it being a wavelength and a frequency. Right, this is all stuff that I cover in the video content. But that's considering light as a wave. It has a wavelength, and then that wavelength has a certain periodicity, a frequency. And we can detect different wavelengths of light by the color that we detect the different wavelengths of light as different colors. All right, our eyes are electromagnetic detectors. Okay, and there's a small range of electromagnetic radiation that we call the visible range that we can see these colors. And so when they burn the hydrogen gas, refract it through a prism, we detect these 4 different colored spectral lines. Those then are translated back into wavelengths and frequencies. We can measure those. And you'll be doing this in lab next week. In lab next week, you're going to take the wavelength that we're measuring in nanometers. Right? Nanometers is 10 to the minus 9th meters, for those of you who don't know. Okay. And we can translate that into what the frequency of that light is using other principles and equations that I cover in the video content. All right, but for the point of this experiment, this was pretty neat in and of itself. We only have 4 spectral lines that come from what we call, this is an emission spectrum. Right? This is what we call the hydrogen emission spectrum. That's just 4 spectral lines. I'll put lines in quotation marks because we talk about these as lines, but it's really not a line, right? This is the readout from this experiment. All right, but perhaps a little more amazing is when we do this experiment, instead of taking white light and just refract it like we have up on top, if instead we take white light, here, let's do a little light bulb here. I know light bulbs aren't white light, but you get the idea. And if we shine this first through a canister of hydrogen gas, and then refract that through a prism. So what we're doing now is we're first passing that light through hydrogen gas and then see what comes out. And we see something pretty amazing in that experiment. We still see the full spectrum of light that we saw with white light. But now we have 4 specific lines that are missing, 4 dark lines, only 4. And if you're really, really careful, you can actually match those 4 black lines with 4 of these hundreds of dark von Fraunhofer lines in the whole spectrum, okay? But when we do it just with hydrogen gas, we only get these 4. These are what we call the hydrogen absorption spectrum. What gets absorbed by the hydrogen? and the emission spectrum, what is emitted from the hydrogen gas. And you probably can already see what's going on here because I've lined these up. The 4 spectral lines from the emission spectrum completely line up with the 4 dark lines that are missing from the absorption spectrum. They are the same. Okay, and that's just for hydrogen. If we did this experiment with oxygen, we'd see the same thing, but the spectral lines from oxygen are different. Each element has its own unique signature of spectral lines. Let's call it a signature of spectral lines. Here on the next slide, you can see this is what it is for oxygen. This is a picture of the aurora borealis, the northern lights. Anyone ever see the northern lights in person? I've never seen it in person, but I'm told it's magnificent. Anyway, it comes from the same principle that we're going to be talking about up above, right? With the hydrogen, right? We're burning the hydrogen flame, right? And we're seeing the spectral lines that come out, or we're shining the light through and we see these spectral lines, they come off as different colors. Same thing is happening with oxygen in the atmosphere. It's being bombarded by radiation from the sun that excites things, right? We're going to be talking about that today. And we get 2 spectral lines out for oxygen. One's in the green range that we can see, and one is in the red range that we can see. If we passed white light through oxygen gas, we'd see a full spectrum, but missing these 2 lines. It's the same principle. All right. So this was really, really interesting stuff, but scientists had no idea why. They didn't have a theory. They can characterize it really, really well. And in fact, people like Balmer and Rydberg here, they can characterize it so well, they can come up with mathematical descriptions of these lines. It's what we call empirical representation. We can empirically define what these lines are and calculate them. And in fact, in your textbook, it takes you through all of that math. Like I said, in this class, we're not going to be doing that. Right? So this is one example that when you're following along in the chapter, when you get to the part about the Balmer and Rydberg series and doing those calculations, don't worry, we're not doing those calculations in this class. Now, if you take Gen Chem 1 from someone else, they might have you do those calculations. But I decided not to, and instead keep us focused on the overall idea that comes from these analyses, all right? So this mathematical description, it was great, it was empirical, meaning we can describe what these lines are, and we can predict where they are, but we still don't know why. There's still no theory as to why. Still no theory to explain why. Why? Why? Why is this happening? What is going on here? And this went on for probably half of a century of research, of doing all of this very, very careful observation and calculations and mathematical descriptions and all of this stuff, still without understanding. There was no model, there was no theory to explain all of this body of information. Okay, so now we're going to come to more scientists are coming in, and they're bringing in data from diverse fields, and sometimes that's what's necessary to come up with the next discovery. Right? I already explained to you down below here where we've been with electrons, okay, and how we thought of those as particles in the video content. I talk a lot about light that behaves as waves. but then also that it can behave as a particle. This idea of duality, the wave-particle duality of light. Again, that's all in the video. All right, we talked in the video a little bit about Max Planck and this idea of quantized energy levels, and I'll talk about that again in a minute. I'll just summarize that. The textbook goes a lot more detail into what Planck did, and it is really interesting stuff, but I'm not going to go into a lot of depth into what Planck actually did. Instead, we're going to talk about the results of what Planck came up with to describe the observations that he was making. Right, but we're bringing all of this into play here. Max Planck, this gave us the idea of the quantized energy levels. Quantized into discrete energy levels, or I'll call these packets. And it really took all of these ideas merging together to come up with the next level of understanding. And in doing so, it's going to explain the mystery of these lines. Right? That came from Niels Bohr and the Bohr model of the atom. By the way, most of these folks won the Nobel Prize for their work. A lot of the experiments that we've been talking about, not like the Nobel Prize is the greatest thing ever, all right? It's pretty important, all right? But there are lots of important discoveries that we've talked about, like Mendeleev, who does get an element named after him on the periodic table, but he didn't win a Nobel Prize. But Rutherford did, Bohr did, a lot of the people in this chapter ended up winning the Nobel Prize. All right, so Bohr comes along. Now, this work was noted in 1913, so it gives you an idea of the time scale, because we started talking about this stuff in the early 1800s. So it took a while, all right, to come up with the next step. But what Bohr did was he took a look at these individual ideas. He took a look at the Balmer and Rydberg measurements, right? All those measurements, the math that we're not going to do. They were very good and predictive measurements. They just didn't explain where they didn't explain the underlying mechanism. All right. You took Max Planck's idea of quanta. Quanta is the word that Planck came up with to describe these packets of energy. And if you want more information on that, like I said, I cover it in the video content. You can read about it in the chapter as well. Excuse me. And also, Bohr took a look at all of this spectral lines information that I summarized for you on the previous slide, in particular for the hydrogen atom. And the Bohr model is for the hydrogen atom, and it explains the hydrogen atom very, very well. So here's the Bohr model for the hydrogen atom. So hydrogen, how many protons are in hydrogen? One proton. So I'm going to put, and we know where the protons are. They're in the nucleus, which is at the center. So I'll put a plus charge here, one plus charge at the nucleus. How many electrons? One electron. So all we need to describe is the behavior of one electron in hydrogen as it's being excited when you put it in the flame, and then maybe as that excitation goes away, and then the electron will lose energy, and it will, what I like to say is, fall back to a lower energy state. And Bohr imagined that these different energy levels were quantized, and he's calling them n equals 1, n equals 2, n equals 3. N equals 1, this is what we call the ground state. The ground state is the lowest energy level, where things are most stable. Okay. And now, if we go back to the Kirchhoff and Bunsen experiment where they ignite the hydrogen gas, now you've got a flame. So we're adding energy to all of these hydrogen atoms. So we're going to take the electron that's here in the ground state, and it's going to get excited. Now, you might think that the flame is pretty energetic, and all those electrons are just going to go flying off into infinity and never returning back to the atom. Turns out it takes a lot more energy than the flame has to get those electrons to leave the hydrogen atoms. So they're actually still part of the atom, all right? They're not forming ions. They're just going to get excited to a higher energy level. And then while still in the flame, they can lose that extra energy. And then in doing so, the electron's going to fall back down to these more stable, lower energy levels. But first, let's talk about what happens when it gets excited. So here's that electron, okay? And it's going to get excited, and maybe it will jump up to n equals 3. Here we have an excited electron. It's now found at a higher energy level. Now, when you review the idea of Max Planck's quantized energy levels, here I'll describe it a little bit, right? Because I think it's important for you to know what's going on. The idea of quantized energy levels is, for example, let's look at these steps here in the lecture hall. I'm taking this with me so it still records me. All right. I'm now on the ground floor, so I'm in the ground state right now. Okay? But as I go up here, now I'm at n equals 1. All right, I've just climbed a step. Now I'm at n equals 2. But I don't go from 1 to 2 until I have enough energy to make it to 2. So if I have more energy than I need to stay at 1, I'm still going to be here at level 1 until I reach the next quantized energy level that allows me to get to 2. And then instantaneously, I leave 1 and I'm found at 2. I'm never found in between the steps, okay? There's no sliding scale of energy levels. You're either at one place or you're at another place and never in between. So it's quantized. You don't take the next step until you have enough energy to get there. So that electron won't leave n equals 1 and jump up to n equals 2 or n equals 3 until it has enough energy to do so. That's the packet of energy, the quantized energy level. Now, it takes energy to make it up that way. And remember, electromagnetic radiation, that's energy as well. So that's going to explain the disappearance of some of these spectral lines, because that energy went into that electron getting excited to a higher energy level. So one of these lines is going to correspond to that electron jumping from n equals 1 to n equals 3. That energy is gone. It got absorbed into the atom, all right? If it's absorbed into the atom, that means it doesn't make it through to our detector for us to see as a color of light. It's gone from the spectrum. It got absorbed. That's why we call that an absorption spectrum. So this absorbs the electromagnetic radiation. That's going to correspond to one of the dark lines in the absorption spectrum. But at some point, even though it's still in the flame, it's going to lose that energy that it just absorbed. And when it does so, it's going to, what I like to say, fall back, all right, or drop down, all right? So that same electron is going to lose energy. And it falls back to a lower quantized energy level. And when it does so, it's going to give off that energy. It's going to emit the energy. It's going to emit electromagnetic radiation that, again, we can see as a characteristic wavelength and a characteristic frequency. Remember, this is all wavelength times frequency. So we can see it. In fact, we have a name for these things. Anyone know what the names for this packet of energy that's released that we call this? It's called a photon. Very good. All right. Short for photoelectrons. This is what a photon is. A photon is that packet of energy that is released when an electron loses energy in this quantized way. So we might talk about photons of light, which when you're thinking about light as a particle, you might think of that as a particle of light. Just like a molecule is the unit of a compound, the photon is the unit for light. If we were thinking of light as a particle, right, our units of light are photons. Yeah, you had a question?
Yeah, I just want to make sure, but then eventually they lose energy and thus they come over.
Yeah. To emit light. Yes. Did everyone hear that question? When it's in the plane, right, the light that's emitted, that emitted light doesn't happen until the excited electrons lose that excited energy as they're falling back down to the more stable energy levels. Then the light is emitted. All right, so I've been dancing around some of this equations that I talked about in the video. Wavelength, I use the Greek letter lambda for wavelength, and frequency, I use the Greek letter nu for frequency. All right, and many of you who are taking physics right now probably already know this relationship, excuse me, that the wavelength times the frequency is equal to the velocity, and I talk about that in the video. But if we're in a vacuum, what's that velocity? Who knows? The speed of light, c. Anyone know what the speed of light is? 3 times what? 3 times 10 to the 8th meters per second. It's actually a little bit less than that, but 3 is good enough. All right. 3 times 10 to the 8th meters per second. And you'll be using all of this stuff actually next week in lab. There will be math involved, but it's going to be in the lab component that you'll be taking next week. All right, so we've got this equation, and from Max Planck, he already was working on this idea of quantized energy levels, and he came up with this relationship that the energy of a photon is going to be directly related to its frequency and quantized by the Planck constant, which is actually written right here. This is the Planck constant. This shows you how those packets of energy, what the packet actually is. 6.6 times 10 to the negative 34th joule seconds. That should be an exponent there, 10 to the minus 34. All right, so E equals h nu. The energy of a photon is directly related to the frequency of electromagnetic radiation, quantized by Planck's constant. Well, frequency of electromagnetic radiation. Now, it's easy for us to see the colors of light. Like I said, our eyes are electromagnetic detectors, but what we see is the wavelength. Right? The wavelength is translated into the colors, not the frequency that we can detect, but it's a quick rearrangement and substitution of this equation. Right? If I take this one and just solve for nu, right? Nu, the frequency, is equal to c divided by lambda. That's just simple algebra. And then I can use that to substitute into this one, right? If I substitute that in, I'm going to get this very useful relationship. The energy of a photon is directly related to 2 constants that I don't have to measure, Planck's constant and the speed of light, divided by the wavelength. So I can actually now visualize the wavelength and directly relate that to what the energy of that photon is. Right? We can easily see wavelengths as colors. And that's going to allow us to identify what the energy is. And this energy, this is going to be the difference in energy levels between the quantized energy levels of the atom that we're studying, right? This is going to be the difference, or the delta, I told you there's a lot going on in this chapter, okay? I'm just summarizing it for you. We're not actually doing this math, okay? But I want you to understand where these equations are coming from and how they can be used. In the upper right, we have a diagram here from the textbook. Here's n equals 2, n equals 3, n equals 4, and we have different colored lines. So I showed you one in red here going from 3 to 2. So let's take a look at this. So here's the electron going from n equals 3 to n equals 2. All right. So we're starting here at n equals 3, and we're falling back down to n equals 2. That's going to emit a photon of light that we can measure. And the arrow is colored in red. That's going to correspond to this red spectral line here. This red spectral line right here comes from the excited electron that's at n equals 3 that loses a packet of energy to fall back down to n equals 2. And we can actually, the other arrows are for the other 3 lines that we see. Those are the 4 spectral lines that we can identify in the hydrogen emission spectrum that's missing in the hydrogen absorption spectrum. And they all map down to transitions between n equals 2 through n equals 6, the energy levels there. So this explains the 4 spectral lines that we talked about earlier. Now let me just point something else out right now as a foreshadowing, all right? Notice that the distance between 2 and 3 is greater than the distance between 3 and 4, and that's greater than the distance between 4 and 5, and so on and so forth. This is something that we're going to be visiting a few times throughout this chapter. As you increase the energy level, the difference between the energy levels gets smaller. All right. I'm not going to write that down on the slide now because there's already a lot written down here. Just store it in your short-term memory. We'll be revisiting that observation soon enough. All right, but that's just 4 transitions. What about 6 going to 5, or 5 going to 4, or 5 going to 2, right? There's all sorts of combinations. It's not just these 4, but these are the only 4 that give off electromagnetic radiation in the visible spectrum range. In other words, the only 4 that we can see with our own eyes in the visible range, until we came up with ultraviolet detectors and infrared detectors. There were only 4 transitions in the visible range. But later on, when we came up with those other detectors, we can see, we can make measurements in the ultraviolet range. We can make measurements in the infrared range. So now we've covered all the transitions, all the possible transitions, going up to n equals 6. Okay. Now here are the ones that we were just talking about, and we've named these now the Balmer series, right? After Balmer, all of that math that we talked about earlier. We also have the Lyman series for these ultraviolet transitions, and we have the Paschen series for the infrared. The point of this slide is simply to demonstrate that we can actually detect all of these different transitions in the hydrogen atom. Remember, it's just one electron that's dancing around here. Okay, and I already just mentioned this. All right, the higher the energy levels are, oh, I didn't mention that one. Sorry, I mentioned this one. Right, the difference between energy levels becomes smaller as n increases. And the other thing that's not really shown here, but I'll just mention it, it's in the upper left. The higher the energy level becomes, the further away those electrons are going to be from the nucleus. Okay, and then the rest of these bullet points on here, I already mentioned, although I didn't talk about this infinitely far away. Notice at the very top here, we have an infinity. Yes, there is a certain amount of energy that we can add, right? Notice the left hand, the y-axis here is just relative energy. So as we're adding more energy, we can promote those electrons to higher energy levels. Yes, there is a certain amount of energy where now the electron will actually be infinitely far away. Okay. So this is enough energy to be infinitely far away. That means it's never coming back. It's gone. It's formed an ion. And in fact, the energy that it takes to get there, we'll be learning about that at the end of the chapter. That's called the ionization energy. Whoops. Ionization energy. So the Bohr model explains all of this really, really, really well for the hydrogen atom only. But it doesn't explain the others quite as nicely. We still need to refine this a little bit better. It not only doesn't explain all of the other ones, there's a few other mysteries that it doesn't explain. For example, when the electron loses energy, why does it fall back down to this ground state? Why doesn't it go further? Why does it stop at the ground state? Remember, don't forget what the ground state is here. The ground state is the most stable. But why does it stop at the ground state? Why doesn't it just completely go all the way to the nucleus? Because after all, the electron is negatively charged, right? And the proton in the nucleus is positively charged, and opposites attract, right? So why doesn't the negative charge go all the way down to the nucleus where it's really attracted to? In fact, if it did that, the two charges would annihilate each other. So why not have the electron go all the way to the positively charged nucleus? Why does it stop? Okay. So there's still some important questions left from the Bohr model. Great as the Bohr model is at explaining everything that I've just told you about today, including the behavior for hydrogen, it still doesn't answer these questions. But it didn't take too long for this fellow to come along. Louis de Broglie is how you pronounce that name. It's not de Broglie, it's Louis de Broglie. He comes along, all right? This was only around 1924, so it wasn't too much further along, okay? And he was looking at what Einstein did, right? So all those hundreds of years, or almost 100 years, where scientists thought that light behaved as a wave, and now it's a particle, okay? So de Broglie's thinking, well, all this time we're thinking of electrons as particles. What if we thought about electrons behaving as waves? So why can't electron also behave as a wave? Now that's a hard thing to kind of imagine, right? How can an electron behave as a wave? He's calling these things matter waves. And in fact, he came up with a very neat mathematical description of those matter waves. Here's the wavelength of the matter waves. Lambda is for wavelength. Here's our friend Planck's constant. So things are still quantized. And then this term down here, this is simply the mass times the speed, which collectively is the momentum. But the important thing about de Broglie's matter wave equation is that we can predict what the wavelength is, and it's inversely proportional to the mass. All right. Yes, there's speed in there as well, but we got Planck's constant, but it's the mass. So according to de Broglie, everything behaves like a wave. All matter behaves like a wave. The planet Earth circling the sun, all right, is actually doing so as a wave. We just can't measure that wavelength because the mass of the Earth is pretty large, right? And that mass is in the denominator. So it's going to make the wavelength way too small for us to measure. All right. So the mass of large objects is too large to then measure the wavelength. Okay. But the electron, the mass of an electron, that's so small that we actually can measure this wavelength. Okay. Everything moves in a wave, just cannot see with large. So that's what I just said right here, right? But electron mass is very small. So now this wavelength starts to make sense. But what is a matter wavelength? Diagram here. Let me switch to a simulator here. All right, here's a simulation. You don't have this in your notes, so you can just watch. Here we have, here, let's do this. Let's go to no end, and I'm just going to pulse this. And here's a disturbance wave, okay? It goes up and it goes down, right? And then the wave translates and it goes out the window, okay? That's what we call a disturbance wave. If I now fix the end here and I bounce it, it's going to hit there and it's going to bounce back, okay? See what's happening there? That's just, and then it kind of goes back until it dissipates. Now I'm going to oscillate this up and down, okay? Now, you might look at this and say, oh, I can see the waves moving across. Well, it would be moving across if I open the window, right? Now it's actually going out the window, okay? But we want to use this model to describe how electrons are stable in an atom. It's not a perfect simulation of electrons, right? But I think you'll get the idea. So let me fix the end here and restart this. Whoops. They're actually not moving across. If you focus on here, if I just focus right here where the peak, where the valley is coming, it's always coming at the same place, all right? And the peaks are always coming in the same place. If I stop this at just the right place, let's see. That's good enough, all right? So the disturbance is almost right here at the midline, all right? Now imagine, not like this, but take the two ends and wrap them around each other, okay? And now what you have is, follow the phase here. It's going up, down, and then it goes up. And now we're wrapping it around. So as it comes up here, it continues to come up here. It's in phase. Do you see that? If this were a circle, this wave is in phase, and it will be continuing going around and around and around because there's nothing to stop it from just going in phase like this. As opposed to, let me slow this down. Let me change the frequency down to, say, 1.25. Start this up again. Right? It looks about the same. It's going a little slower because the frequency is slower. Right? Up, down, up, down, up, down, up, down. Stop it at about the same place. Okay? Now it goes up, down, up, down, up, down, and as we circle it around, it's coming down here, but wait a minute, it's going up here. It's no longer in phase. So if this were an electron traveling as a wave, it's no longer in phase as it's circling around the nucleus. So there's some frequencies where it's in phase and it's stable, and there's other frequencies where it's not in phase and it's unstable. I can go back down to, let's say, 1.00 here. start it again. Now, each time I do this, I haven't pointed out, we haven't actually counted the phases. But notice now it's back in phase. Look at how many cycles we have. We've got one cycle, so I'm calling a cycle going from one place in the cycle to the same place the next time around, right? So up, down, up, that's one, up, down, up. So that's two phases, or two cycles in the phase, all right? If I go back up to 1.5, where it was also in phase, and try this again, I needed to restart it, or else it's all jumpy. Okay. Now it's in phase, and we've got 1, 2, 3 phases. Quantized, right? N equals 1, N equals 2, N equals 3, and so on and so forth. Okay? So that's kind of the essence of what Louis de Broglie was trying to show. If we think about things traveling in a wave, all right, and a wave, we can measure a wavelength, right? The wavelength is the distance between the two same parts of the cycle. So here's our wavelength. So peak to peak, or valley to valley on the wave, okay? And if we follow that along here, let's say this is an electron traveling as a wave. Here, I need a different color so this shows up. Here we have N equals 3, a nice quantized N equals 3, all right? And I'm gonna trace out 3 wave cycles that are going circularly around the nucleus. That's not drawn in the center of this, okay? So just follow along here. It starts in the up position and it goes down and then up again. And that's one cycle. Down, up, that's cycle 2, and then down, up, that's cycle 3. And when I'm done with that third cycle, I am back in phase where I started. So if I kept circling around and around and around the center here, as long as I've got this particular wavelength and this frequency, it's going to always stay in phase. So it will always be in a nice, neat N equals 3, and it will keep going and keep going. Whereas if we have N equals 2 1/4, all right, let's start up here at the top. We'll go one cycle, down, up. Okay, so that's one cycle. Oh, here, I have to start somewhere else, sorry. Let's try that again. Let's follow along here. Let's start down here, start at the center. So up, down, up, that's one cycle. Up, down, up, that's a second cycle. And now, when we're back to where we started, we're not in the same phase. We haven't completed the cycle by the time we've made it around the circle. Okay? So the idea here is that there's only certain wavelengths that will allow you to stay in phase as you're traveling like a wave around this circle. If I were to draw this from above, right, let's looking down on it, right, for N equals 3, I would draw maybe a wave that looks like this, 1, 2, 3, and we stay in phase. And the next time we get in phase is when we're at N equals 4. Now I'm going to have 4 waveforms, 1, 2, 3, 4. But anything in between those two numbers, by the time I get back around the circle, I'm not in the same phase. And so it's disorganized and it's not stable. That's the idea behind these matter waves. And it actually explains a lot of those unanswered questions. It explains the ability for these electrons to stay stably at the ground state and not simply just fall into the nucleus, because they're not stable. That's not a stable orbit for the electron. The only way that it exists stably is for it to be in one of these quantized matter wave arrangements. All right. Now, it doesn't maybe seem all that fantastic to you. And in fact, he did this as a graduate student, okay? And his thesis committee didn't believe any of this. And his thesis was only like 5 pages long. And they're like, what's with this guy? This is a crazy idea. I mean, just look at him. Would you believe that face? No, all right. But so anyway, his thesis committee sent the 5-page thesis off to Albert Einstein to get his opinion. And Einstein took a look at it and he read it and he wrote back and said, yeah, maybe. And so they gave him a PhD, okay? And he got his PhD, all right, in 1924. And then 5 years later, In 1929, he wins the Nobel Prize for this work. Okay, that's how revolutionary this idea of matter waves was. This opened the door to really understanding and coming up with quantum theory, which is going to be what we're going to cover in the next lecture. Okay, so his contribution was really important.